This lesson is on the basics of something called stoichiometry. Yeah, nice, cool name to call these types of math or analytical chemistry type problems. So, stoichiometry is built on the idea that we need to have a chemical reaction and we need to balance that chemical reaction in order to know how much of each element or compound is needed to make this reaction work ultimately the best that it can. As we've looked before, the reason that we balance chemical reactions is to find something called coefficients. And these coefficients tell me something called mole ratios. Any balanced chemical equation, by following the law of conservation of mass, we're going to find this ratio. And these ratios will help us not only figure out how much of each element we need to go forward in a reaction the best, but it'll also tell me how much of the products we'll make, comparatively speaking. So without trying to explain all of the power in stoichiometry, and I'm not saying that to be tall, I'm saying that there is true power in these types of reactions because now we're doing real chemistry. So the first step, in order for me to answer questions that are about different atoms or different substances, let's explain. Look at number one. How many moles of carbon dioxide? So in this question, they're asking how many, because a mole is a how many number, are formed when 40 moles of oxygen is consumed. So notice something. I'm starting you with information about oxygen, which by the way is 40. Okay, let's connect this arrow. There we go. And I want to know how much carbon dioxide I should make. Now, of course, this question really should say, assuming I have an unlimited supply of methane. So look at this. I'm asking about how much CO2 I should make if I start with this amount of ingredients. As I keep referring to this good cake, all right? If I have the right number of eggs, how much flour do I need to make a certain number of cakes? So what's cool about stoichiometry, once we have the balanced chemical reaction, once we know how many of each of these is needed to be produced or made, we can start answering questions about other chemicals linked by these ratios. So we're able to, let's say, hey, not only do I want to figure out how much methane to oxygen do I need to have the best reaction, the most explosive reaction possible, but I can also figure out exactly how much water I will make if I have these ingredients. That's pretty powerful. Not only that, I can figure out, let's pretend that I want a certain amount of a product. Let's say I want 100 grams of hydrogen. How much methane and oxygen do I need to make that certain amount? And you can see the power here. Now we can figure out, with information from one element anywhere in the equation, we can answer something about another. So let's stop talking about it. Let's do it. All right. So let's balance first, because in order to do and use the ratios of how many of each of these elements in a reaction, we have to know them. So we have to balance first. Okay, one carbon, one carbon. 4 H's on this side, the reactant side, we have 2 H's. So I'm going to put a 2 here. That gives me 4 H's, and I have, or 4 hydrogens on the what? Product side, and I have 4 H's on the reactant side. Now, my carbon is balanced. There's one carbon and there's one carbon, and my oxygens are not balanced yet. Okay, so if I look on the product side, I have 2 plus, that's right, 2, so I have a total of 4 oxygens on the product side. I only have 2. In order to have 4 atoms of oxygen on the product side, a reactant side, I have to put a 2 here. 2 times 2 is 4 oxygens, and 2 in front of the water makes 2 here, and there's 2 in the CO2. And now I'm balanced. Okay, if you want to put the 1's in, you can. All right, but you should know a methane implies 1, but we'll put that one there. So look at the ratio, party people. We have a 1 to 2 to 1 to 2 ratio. Why is that important? Well, that's important because now, knowing how much methane I have, I know that I'm going to produce twice as much water as methane molecules I start with, assuming I have what? Enough oxygen. And of course, I can answer many types of questions. Let's do that. Number one, how many moles of carbon dioxide? So we're asking about how much CO2 is formed. What are they giving me? They're giving me 40 moles of oxygen. So, given 40 moles of oxygen, let's just write it. Always start with the number given, so 40 moles of oxygen. Okay, and notice I'm keeping the E off because I want to reduce the amount of time talking about MOL. So, in any case, if you're cool, we take the E off, 40 moles of oxygen. Notice this is in atoms now, this is molecule. Okay, and I want to get rid of, and this is the first time we do this, I want to get rid of not mole, but I want to get rid of oxygen. Because they gave me 40 moles of oxygen, but they want how many moles of carbon dioxide? So my friends in chemistry, I put CO2 up here. That's the compound I want. But what's the converting factor? My friends in chemistry, the converting factor is the mole ratios, is the coefficients. So for every one CO2, there are 2 oxygens. It's an easy math problem. And what we have here is 40 times 1 divided by 2. We have, of course, 20 moles. That didn't go away. And I have CO2. Of course it's that way. It's a 1 to 2 ratio. It takes twice as much oxygen, okay, to produce half as, I'd say it produces half as much CO2 than oxygen because it's a 2 to 1 ratio. Okay, let's go on to number 2. How many moles of methane? That's what they're asking about. How many moles of methane, that's what we're going to end up with, is from 200 moles of water. Okay, well, same thing. Start with the number they give you, 200 moles of water. Now, when you do these types of problems where you're using the chemical equation or the chemical reaction, the balanced chemical equation, you should be writing the not just the number and the unit, but what it represents. So 200 moles of water should be written there. Now I'm going to get rid of water because what are they asking for? They're asking for methane. All right, well, methane goes up top, CH4. And what's the ratio? There is 1 methane per 2 waters. And you can see the water cancels, and I'm left with 200 times 1 divided by 2, cutting in half, obviously, is 100 moles of water. Now you certainly could have been doing this problem without all of this dimensional analysis by looking at it's a 1 to 2 relationship. So if I'm starting with water and I have a value of it, in this case 200 moles, guess what? I have half that amount because it's a 2 to 1 ratio. So we're using these coefficients. But understand these coefficients are how many, okay, ratios. They're not a how heavy. These are ratios of how many. That's why I can use what? Moles going to moles. All right, notice they started you with moles and they wanted moles. So because this is a ratio of how many, as we've already established and we've already balanced with the hydrogen and oxygen reactions, then if you give me a how many equivalent or value, I can just do one step because I'll say it again, this is what makes it stoichiometry. Using the mole ratio somewhere in your problem makes this stoichiometry, where I give you information about one compound and you answer by another using these how many ratios. So we'll leave 3 blank, okay, so you can do that one on your own. Let's move on to the next number 1. And we have a new unbalanced equation. We have to determine the mole ratios in order to answer questions from one chemical to another in this chemical reaction. So we have 3 carbons, we have 1 carbon, so we're going to throw a 3 in there. Okay, I have 8 hydrogens and I have 2 hydrogens, so I put a 4 in front. 4 times 2 is 8. No other place on the product side, right? This is the product side. Do I have hydrogens? Now, I got to balance my oxygens. Here I have 2. Here I have 3 times 2 is 6 plus 4 in front. 4, that gives me 10 oxygens. How can I make this 10 on this side? Well, I have to put a 5 in front. And lo and behold, or high and behold, if you're me, okay, we have our balanced reactions. Put the 1 in front if it makes you happy. Makes me happy. Okay, so number 1, let's see what they're asking. I bet it's a stoichiometry problem. How many liters of oxygen, that's what they want, are needed to produce 600 liters of carbon dioxide? That's what's given. So, as I said before, if you have no idea how to do this, start with the number given. So I have 600 liters of carbon dioxide. Alrighty. Now, what do I do here? Well, I want to times it by this mole ratio. At least that's what I think, right? Because in previous problems, we would take in the number given, we times it by the ratio. But what I said before is you have to be careful. Make sure the unit that you're using is appropriate for a how many ratio. So if I'm going to get rid of CO2, CO2 goes in the bottom. And I'm asking about oxygen, it goes up top. Okay, it's not atoms, it's O2. And if you can see here, there is 5 oxygens, right? Getting it right from the balanced equation. From what? 3 CO2s. Okay? Now the question is a liter or a volume a number that I can use with this ratio, with this mole ratio, how many ratio? The question really is volume or liter or milliliter, okay, is that proportionate to how many? And I'm hoping you scream to me somehow that I can hear you. Yes, of course it's proportionate. Avogadro's hypothesis, if I have what? Equal volumes of 2 different gases, the same temperature and pressure, I have equal number of molecules. Double the volume, double the number of particles. So I can multiply this directly by the ratio, my friends in chemistry. So 600 times 5 divided by 3. And I get 1,000. 1,000 liters because that's the only unit left standing. Now it's liters of oxygen. You should always make sure you know what you're talking about. So now not only do I need a number now, I need a unit and of what element, what compound, element, or substance, because we're changing from one substance to another. Using what? The ratios of how many. So notice my answers all have the number, the unit, and what chemical I'm talking about. Very important now. Okay, you keep track of that. All right. So the next question is very similar. I'll leave that for your homework as well. Okay. It's the same idea. If you notice, I'm starting with millimeters, and you want millimeters. This is a volume. This is a volume, and volumes. And guess what? This mole ratio are proportionate. All right. So I would like you to do number 2, number 3. We're going to leave 4 for another time. All right. And we're going to go to the back side now. Okay, the back side, we have a metal plus hydrochloric acid gives me metal chloride and hydrogen gas. This should look very similar to the reactions I've been doing to produce hydrogen in class. Okay, so before we can continue with these types of problems, we have to balance the equation. So 1 magnesium, 1 hydrogen, 2 hydrogens. Oh, well, put a 2 in front. That's 2 chlorines. Oh, there's 2 chlorines. And lo and behold, we're happy and we are balanced. Hopefully all of the above. Now, number 1. How many grams, that's what we want, of magnesium are needed to produce 100 grams of hydrogen? Whoa, okay. So what am I given? Well, as before, write down what's given to you. 100 grams of hydrogen. Now they want grams of magnesium. Well, so it makes sense from everything I taught you, you would do this. Get rid of hydrogen. Put magnesium. There's 1 magnesium for 1 hydrogen. This reaction should look very familiar to us. Didn't we put this in a Stiochiometry too, right? We put a little copper holding on to a little copper wire. We had some magnesium, and then we put hydrochloric acid, inverted it, and we collected some gas. Yeah, this is the same exact reaction. How did we come up with moles of hydrogen? I told you way back when, it's because the same number of moles of magnesium. It's a 1-to-1 relationship. So this is something we've already learned. But, hey, back to the problem. 100 grams of H2. So this sounds like something I would have, and it looks like to me that I'd have 100 grams of magnesium. I hope you're all screaming, no, of course is not correct. This is not correct because, number one, this is not a how many number. Grams is a weight number. It's a how heavy. And we cannot take a how heavy number and times it by a how many number. That is not going to work. And the reason it doesn't work because every element has a unique mass. So we cannot do it this way. When we were doing the other problems, if you remember, okay, if your short-term memory is not as gone as mine because of the height, you know that this was a mole to mole, one step. Well, a mole represents how many, and this is a how many equivalent. So you could do that. The other question we did was liter to liter or volume to volume, and we did that because volume, because of Avogadro's hypothesis, is proportionate to a how many number. But a gram is not. We need to convert from grams to how many first before we use this ratio. So what we do, party people, is we now first convert this into a unit that we can use into that ratio to get rid of my hydrogen and get magnesium. So first step, how do we convert to how many number? We convert to moles. 1 mole of hydrogen is 2 grams. How do I know? Each hydrogen has an atomic mass of 1. There's 2 of them, formula mass or molecular mass. We've got 2 grams. Now, this expression represents moles. Do not find that number, although I know you can get it in your head. Continue on with the problem. Okay, grams go bye-bye. Now I've got, let me get rid of that hydrogen crossed off. Okay, now I've got this whole expression right here is moles of hydrogen. Okay, and when I get rid of hydrogen, so I'm going to put hydrogen right here. And I want what? I want magnesium. So magnesium comes here. Now I put the ratio. There's 1 magnesium to 1 hydrogen. Mr. Zagrodsky, it's a 1-to-1, so it's not needed. I get that for this problem. However, I want you to do this for good bookkeeping, to keep everything nice and organized so you don't get anything wrong. I'm going to get rid of my hydrogen. The whole part of the problem is to get rid of I have information about hydrogen, and using that how many information about hydrogen, I should be able to relate that to how many of magnesium because of the law of conservation of mass. So now, by doing this, this whole expression right here represents not moles of hydrogen anymore. Now it's moles of magnesium. And I say that to you because if the question stated how many moles of magnesium were needed or produced or needed to make 100 grams or to produce I'll say that again. If I was to word it this way, this expression represents moles of magnesium. And if the question asked this, okay, now I got it. How many moles of magnesium are needed to make 100 grams of hydrogen? You'd be done. So this right here is moles of magnesium, but that's not what they asked. They asked for grams of magnesium. So we keep going. The next step is to convert my moles of magnesium. These are the only units and chemicals left standing. Get rid of mole. Where does mole go? Well, the mole's on top, 1 mole on the bottom. And I want grams. Grams of what? Well, because hydrogen's gone, all I got is magnesium now. And I go to the periodic table. Okay, the atomic mass of magnesium is 24. You can round. And now I'm ready to go. Moles cancel. Everything cancels except for grams of magnesium. I'm laughing at myself. So let's go. 100 divided by 2 is 50. Times 1 divided by 1 is 50. 50 times 24. Okay, and what I get is 1,200 grams of magnesium. So this is called a mass-to-mass problem. Okay, I couldn't go directly. Remember, what makes it stoichiometry, okay, is what? Is that right there. All right, so you should try number 2 for homework. Okay, well, let's go look on some other ones. Look at number 3. I'm just going to read these out and see if you can think with me. I have 500 grams of magnesium chloride. That's what's given to me. Okay, all right, so I think given to me, I'm using this color. How many grams of hydrogen would be produced? So they're looking for grams of hydrogen produced. But they're started with 500 grams of chlorine, magnesium chloride. How many steps? Well, if you give me 500 grams, can you first think you have to go to, let's say, what? Moles. And then times it by the what? The ratio. But because you converted the moles and the ratio, you're still left with moles. You convert back to what? Grams. So how many steps is that? They'll be converting to moles, which is one step. Okay, timesing it by the ratio is the second step. And then converting to grams is the third step. It's a mass-to-mass problem that we had above. Okay, look at number 4. How many grams of magnesium, looking for grams, is needed to react with 1.4 moles of hydrogen chloride? So we're starting with moles, hydrogen chloride. How many steps do I need? Can I times the mole by the ratio? Yeah. And then can I convert my ratio to grams? How many steps? 2. So you can read these problems now and hopefully see how many steps are needed. Look at number 5. How many grams of magnesium is needed to produce 20 liters of hydrogen gas? So I'm starting with liters. And what do? Can I times that directly by the ratio? Absolutely. That gives me liters of the other gas. But now they want grams. So I have to go from the ratio, which is now in liters, into grams. Now you can convert to moles first, and then grams, which would be 3 steps. And that'd be one way to do it. And then number 6, how many molecules? Hello, how many molecules? This is the exact number of stuff. This is Avogadro's number from 100 grams of magnesium. So I have grams. I've got to go to a number I can use that goes into the ratio called moles. Then from there, okay, I can convert that to my ratio, because now I'm in a number that is, guess what, equivalent or proportionate to how many moles. It's what moles is based on, how many. And then from the ratio, convert to Avogadro's number, or use Avogadro's number. How many steps? Convert to moles, okay, times it by the ratio, and then convert it to the exact number that a mole represents. Okay, so I didn't do these for you, but I hope you can see by reading the question, okay, at some point in the question you're going to have to times by the ratio. So try the rest of the worksheet except for number 4. Hope that helped, and look at the key to review.